Finishing out where we left off yesterday on 1-4, okay, as a quick recap, we talked about all the parent functions, absolute value, square root, quadratic, cubic, cube root, and reciprocal functions. And then we talked about the vertical shift, so if we add or subtract after the function, it causes a vertical shift, adding up, subtracting down. Then we did our horizontal shift, and this happens inside the absolute value, or inside the square, or inside the parentheses, and this causes a shift right or left, opposite that your brain thinks. So if it's positive, we go to the left, and if it's negative, we go to the right. Then we talked about a reflection, okay? And the reflection happens if it's in front of the function, not inside the function with it. It's a flip across the x-axis, which takes that curve or whatever it is, flips it upside down. And if it's inside the function, it's a flip across the y-axis. We also talked about that if the negative is inside and there's a horizontal shift, it switches the direction, right? So if I had f of x equals the square root of negative x plus 1, when I describe these transformations, there are two separate transformations. Underneath, the negative causes this to be a reflection over the y. And the positive one is a shift to the left one. So if I separate them out, there are two separate ones, right? But we said instead of separating them out, we can actually combine them together and allow this to change the direction of that shift. So on a square root, instead of going to the left, I would go to the right. But on a square root, instead, because it actually flips the direction, it points left. So you're going to shift it right, but you're going to point it left. On an absolute value, you flip it left to right, it doesn't matter. Squared, it doesn't matter. The horizontal shift is going to change direction, but the physical shape of my graph doesn't matter. Whereas a square root, it will, okay? Then we work through the reflections and we left off on dilations, okay? So a dilation is what's called a non-grid translation or transformation, okay? Translation is sliding. We're sliding right, left, up, down. We're flipping it upside down, but the physical shape doesn't change, okay? It just moves around. In dilations, we physically change the shape. We stretch it or we shrink it, okay? The first kind is a vertical dilation. And a vertical dilation, put your hands like this. A vertical dilation is a vertical stretch or a vertical compression. So if you could think about a V being in between your hands, okay, and I compress it, what's going to happen to the sides of that V? They're going to get wider, okay? If I pull them up, what's going to happen to those sides? It's going to get more narrow. So the shapes go wider or narrower, okay? If it's a square root function, it flattens it out or it stretches it taller, okay? If it's a parabola, it's the same as the V. If it's what am I missing? Like a reciprocal function, you almost see no difference, but it would just stretch it, okay? What causes a stretch is a number on the front of your function that is bigger than 1. So if I had something like 2x squared, this is a vertical stretch, okay? And it makes it narrower. It actually makes it twice as narrow if you think about the actual value that's there. Now notice this says absolute value because I'm not looking at the sign. The sign causes a reflection. So a -2 would be a reflection and a stretch. If the number on the front of your function is in between 0 and 1, so we're talking a fraction or a decimal, then it causes it to be a vertical shrink, which would widen it out. So that would be like a 1/2 x squared. So if I were to plot these both on the same grid, my normal graph, the normal parent function starts at 0, 0, goes up 1 and out 1 for my parabola, okay? If I was to graph the stretch, then instead of going up 1 and out 1, I'm going to go up 2 and out 1. So it's going to make it more narrow. And if I wanted to graph the 1/2 on this same graph, then instead of going up 1 and out 1, I go up 1 and out 2. And it makes it more wide. I don't need these to be perfectly stretched. What I do need to know is you intended it to be narrow or you intended it to be wide. So if you put it on the same graph, like the homework, it's going to ask you to overlap 3 graphs on the same graph. I should be able to see your stretch and shrink that way. But on the test, let's say it just says graph 2x squared. I need to know you intended that to be narrow, so you will literally just write narrow next to it, okay? Make it narrow, but also write that for me. And if you intended it to be wide, you would write wide next to it so that I know, okay? So bigger than 1, vertical stretch, less than or in between 0 and 1, vertical shrink. Now here's where it gets confusing because the horizontal says the opposite thing but almost does the same. So if it's a horizontal stretch or shrink, it happens inside the parentheses or underneath the square root or inside the absolute value bars. So now it's going to look like 2x squared like this. And the wording on this is actually a horizontal shrink. But now do this with your hands. Now you've got walls around your graph. What's going to happen if I shrink my walls in? What happens to that graph? It gets more narrow, right? Or gets stretched further. So a horizontal shrink looks like a vertical stretch. Whereas if I take those horizontal walls and I pull them out and I pull the graph along with it, what's happening to the graph? It's getting stretched wider. So a horizontal stretch is like a vertical shrink. So they are opposites, okay? The wording is opposite. So if it's a number bigger than 1, it is called a horizontal shrink, but again, it will make it look more narrow. And if it is in between 0 and 1, so it's a fraction, like 1/2 x squared, then it's called a horizontal stretch, but it will make it look wider. So the effect is almost the same. It's not identical, but because we're approximating, it's okay to say it looks the same, okay? But the wording is opposite. Vertical stretch is the same as horizontal shrink. Horizontal stretch is the same thing as a vertical shrink. All right, this is why it's different, okay? If you look at this first graph, the solid line is your original graph, okay? Does the dashed line look like a vertical stretch or shrink or a horizontal stretch or shrink? Did the vertical change at all? No, what happened? The walls caved in on it, right? The walls cave in, that means this would be a horizontal. And it would have been a horizontal shrink or compression. Which means that inside the parentheses was something bigger. Well, this isn't whatever the power is. Let's say it's still third. Whatever it is, that is causing a horizontal shrink, okay? Was bigger than 1. Now look at the second graph, and let's say the red is the original and the blue is the translated one or transformed one. Do you think this is a horizontal or a vertical dilation? Vertical. And what do we think happened? Vertical stretch. So this would be a vertical stretch. And it could be something like 2x to a power. It would actually be 3, but we're not going to count it yet. We're just trying to approximate it. Okay, so you see the visual difference, yes, but when we're approximating it, we are just approximating it. So it just needs to be narrow, wide, for stretch and shrunk. All right, so example 3. If I were to describe this transformation, 3 on the front causes what? Is it a vertical or a horizontal dilation? If it's on the front, it's vertical. If it's outside, anything outside is vertical, right? So if there's a number on the outside, it's vertical. If I'm adding or subtracting something on the outside, it's also a vertical. It's just a shift or a stretch. And this would be a stretch. So I would put my point at 0, 0. Something like a parabola and an absolute value, you could get pretty accurate because instead of going up and out 1, you're going up 3 and out 1. But it doesn't have to be perfect. What I would expect to see is either stretch here or the word narrow. next to it here. Go to B. Now it's being multiplied inside. Inside causes horizontal. All right, and that 1/2 means horizontal what? Shrink or stretch? Shrink. No, sorry, stretch. Oh my goodness. Stretch. So I'd start at 0, 0, and instead of going up and out 1, I'd go up and out 2. And if I either say stretch on the top or I'd say wide. So a number bigger than 1, no matter if it's vertical or horizontal, causes it to be narrower. A number in between 0 and 1, no matter if it's vertical or horizontal, causes it to be wider. The only difference is how we describe that with stretch or shrink. It switches. Questions so far? All right, so now we're going to put it all together, and this is what a test question could look like, will look like. Okay, it's going to have multiple parts. A, identify the parent function. And by parent function, I don't mean describe what it looks like. Give me the actual equation of the parent function. So if g of x is 3 plus 2 times x minus 4 squared, what's the parent function? X squared. So f of x equals x squared is the parent function. What does it look like? It's a parabola, okay? All right, B says describe the sequence of transformations from F to G. So now we're just going to literally, I'm going to point out each part of it. So the 3 on the front, what's that causing? Close. It's vertical, but what is it separated by? Plus. So we're not multiplying it, right? We're adding it, which means up 3. It's there to throw you off. That plus 3 could be at the front or it could be at the end. It doesn't matter. It's still going to be a shift up or down. All right, now the 2 that's being multiplied is what? Vertical dilation, specifically a vertical what? Stretch, which is going to make it narrow. The minus 4 inside the parentheses, to the right 4. So now I'm going to take my graph, I'm going to shift it to the right 4, I'm going to go up 3 and plot my vertex. And I'm going to make it more narrow than it normally is. So I'm either going to have the word narrow, I'm going to plot the points, or I'm going to describe it over here, okay? Somehow you need to deliver to me that you were intending for that to be more narrow than normal. Good so far? Yeah. No. It's all. The only thing I'm looking to be exact is your vertex. The 4, 3. You don't need to write it, but it needs to be where it's supposed to be. So I went to the right 4 and I went up 3 and I plotted a point. That's your vertex. All right, then D says use function notation to write G in terms of the parent function. This means literally take out the parent function, which was x squared. So in function notation, in terms of a different one, you never write the absolute value or the square root or anything like that. You write f of x. And f of x tells you whatever this is was my parent function. So I write it in the same order. 3 plus 2 times what's inside the parentheses squared now becomes my f of x. X minus 4 was inside the parentheses. It stays inside the parentheses. So what I have done is replaced my function, which in this case was parentheses squared, with f of, okay? And then whatever's on the outside stays on the outside, and whatever goes on the inside stays on the inside. And the reason they want you to do this is it doesn't matter what my original parent function is. This does the same thing to every parent function. It shifts it up 3. It has a vertical stretch of 2, and it shifts it to the right 4. So this is and you would not be tested on that, okay? But you will need to know how to do it for homework. All right, what's your parent function this time? Absolute value of x. Good. We know it looks like a v, right? All right, let's describe our transformation. So what's the negative on the front? Reflection over x. We know that means it flips it upside down, okay? Okay, inside horizontal. It still makes it look narrow, right? It still makes it look narrow, but the word we would use is horizontal shrink. And the minus 4 inside. Right 4. Okay, so I'm going right 4. I'm plotting that point, and then I'm going to point it down, and I'm going to make it narrow. So again, making sure I wrote the word narrow here or right next to my graph, because I want to know that that was intended to be more narrow than your normal, okay? All right, D. Use function notation to write g in terms of the parent function. So this would be g of x equals the negative still on the front, okay? The absolute value still opens, and now the f goes in, or not the absolute value, f, okay? Everything that's inside here has to be inside my f of. So I open those parentheses, 2 parentheses, x minus 4, close them, and close them again. So those absolute value bars now get replaced with the f of x with the parentheses. Anything inside the bars goes inside the parentheses. Anything outside the bars would go outside the parentheses. We good? Okay. Last thing, and it's not on your notes, but it is in the homework, so I wanted to go over, and it will be on your test, okay, is the reverse, okay? What happens if I give you a graph and you have to give me the equation? That's what this is. So first of all, identify your parent function. What's the parent function? It's an absolute value. Good. Now what transformations are happening here? A reflection over the x. What else? Left 4 and down 2. How do I write that in equation form? I would write g of x equals reflection, means a negative on the front, absolute value, x. A left 4 is what inside the parentheses? Plus 4. And a down 2 is what outside the parentheses? Minus 2. This will never have a stretch or shrink because I don't expect you to be able to figure out exactly what your stretch or shrink is. But it could have a reflection. It could have a transformation left or right. It could have an up or down. Okay? Questions on that one? Okay, for real, we're done now.